So welcome back to the lectures on authenticity. So let's start immediately. What is authenticity? Authenticity is the goal of making sure that information is not tampered with by unauthorized people. So in the previous lectures, we talked about confidentiality, which is when we want unauthorized people, the adversary, not to be able to read our messages, to steal our information. When we talk about authenticity instead, we care about information being authentic and therefore not being tampered with by the adversary. So the adversary in our model, when we talk about authenticity, is someone who can modify the data in transit, or I mean, if you're using authenticity mechanisms to make sure that the data you store has not been tampered with, this could be someone that is accessing your laptop and maybe changing your files while you're having lunch. So the solutions that we're going to study in these and the next videos are solutions based on secret and public key authentication. There is a qualitative difference between secret and public key authentication. So the difference, the gap between secret and public key authentication is larger than we had between secret and public key encryption. Therefore, we use two different names for secret and public key authentication. When we talk about secret key authentication, we talk about MAC, message authentication codes, whereas when we talk about public key authentication, we talk about signature schemes. And the difference will be clear later. So again, let's have a look at the taxonomy and where we are. So when we talked about confidentiality, we had unconditional and computational secure solutions. That's the same for authenticity. We had secret key and public key solution for confidentiality. The same thing holds for authenticity. And in fact, we will see that the techniques that we're going to use in each of these columns will be reminiscent of each other. Yet, please make sure that you're very sharp and very clear about which problem you're solving and which tool you're using. You shouldn't use a hammer to screw a nail. You shouldn't use a screwdriver to hammer a nail. So confidentiality and authenticity are two different problems which are solved with different tools, even though these tools will share some techniques. So for confidentiality, we had the one-time pad, which was unconditional secure. And similarly, we will see some kind of one-time authentication tables, which will give us unconditional security when we talk about authenticity. For confidentiality, we use block ciphers with their modes of operation to get secret key, practical secret key encryption. And here we will have some MAC schemes, and some of them will also use block ciphers and modes of operation. And as an example of public key encryption, we had RSA encryption, and we will see that the RSA function can also be used to construct signatures together with a very useful tool known as hash functions. So let's start with the syntax of secret key authentication. So this is a MAC scheme, and it looks a little bit like secret key encryption, but it's also very different. So the beginning is similar. So we have a key generation algorithm that produces a key, which is delivered to both the sender and the receiver. The key is in a red box, red bubble, which means that it should be kept secret. So the sender, using the key, will compute a MAC on the message. This MAC sometimes is called a MAC, sometimes it's called a tag, sometimes it's called can be called a digest, can be called different things. C here stands for code, not ciphertext. Code. This is not an encryption. This is a code. So this is the message authentication code of this message. And then this is in a green bubble because the adversary might be able to see the ciphertext. Also, very importantly, in message authentication code, we are not, when we talk about authenticity, we're not asking for the message to be necessarily secret. So here the message is green too. There is no problem with the adversary knowing what the message is. So the verification algorithm will take as input the key, the code, and the message, and with output a single bit 0 or 1. So as you can see, the verification is very different from what decryption was in secret key cryptography. The decryption would take as input a ciphertext and the key and output the message. Here instead, the message and the code are given as input, and the output is a binary choice, whether this was the right code or not for this message. So far, so good. We can't talk about security without defining what security means. So let's see what security means for authentication schemes, secret key authentication schemes. So the name of the definition is going to be unforgeability under chosen message attack. So some elements of the definition will remind you of the definition we saw for encryption, but from some other perspective, the definition is quite different. And we'll see that in a second. So if you remember, for confidentiality, the definition of security was an experiment in which adversary could play with two different games, a real game and an ideal game. In the real game, you had real encryption of the real message, whereas in the ideal game, you had encryption of random messages. And the adversary had to distinguish between the two of these. Instead, now that we talk about secret key authentication, the definition of security is a single game. The adversary is playing with a single box. There is no two boxes. There is only one box. And the box does the following thing. The box starts by sampling a key using the key generation algorithm. The key being a secret key scheme, the key is kept secret, is not given to the adversary. But now what the adversary can do is that the adversary can choose some messages. Therefore, the name chosen message attack. The adversary can choose some message and ask the box to compute the MAC of these messages under the key. So this part of the game models the fact that the adversary might have access to a channel and therefore might be able to see what the tag is on a lot of messages. So let's suppose the adversary is sitting between the sender and the receiver and is observing the communication. So all the communication is MAC. So every time the sender sends a message to the receiver, a MAC comes along. So the adversary will collect by eavesdropping over the internet, might be able to collect a large number of messages and the corresponding MAC. So we want to capture this. Again, we like to have our definition to be worst case. So instead of saying that the adversary gets a number of MACs on a bunch of messages which were chosen by the sender, we even allow the adversary to choose which messages he wants to see a MAC on. So clearly, then we're going to have a scheme which is secure under this definition, so the definition in which the adversary even chooses the messages, then the scheme will also be secure in a setting in which the adversary sees the MACs for some messages, even if the messages were not of his choice. We also allow the adversary other queries to this box. This is different than we had in encryption scheme. We also allow the adversary to ask the box for some message and MAC pairs, and then the box will verify, will check whether this MAC and message pair are valid or not, and the adversary will learn the response to that. So these models, in a way, a bit similar to what we had for chosen ciphertext security in encryption. So these models, the ability of the adversary to perhaps submit some message and some MACs to the receiver, and then observe whether the receiver will accept these values or not. So remember that we're trying to solve the authenticity problem, so the receiver doesn't know whether it's getting these messages from the real sender or from the adversary. That's what we're using the MAC for. So the adversary is always able to send some messages to the receiver together with some MACs, and then observe whether the receiver will accept these messages or not. Okay, so that's the first part of the definition, where the adversary interacts with the box. And then at the end of the day, the adversary has to produce a new pair, message 0 and C0. And we say that the adversary wins the game if this M0 and this C0 are a valid MAC. So if the verification algorithm on input K, M0 and Z0 outputs accept. So this means that the adversary managed to produce a valid message and MAC pair. But then, of course, we need to make a caveat, because it's very easy for the adversary to produce a pair M0, C0, which is valid. Well, simply take one of these message and code pair that the adversary got from the box, and then just output that. So that's it's too easy, right? Winning the game like that is too easy. I mean, any scheme will be insecure if you would allow that to be a valid attack. So we exclude that in the first part of the definition. So we say that the adversary only wins the game if he outputs an M0 and C0, such that M0 was not queried in this phase, and that M0 and C0 are a valid MAC and code pair. So we call a valid M0, C0, which were produced by the adversary. Remember, the adversary doesn't know the key. We call them a forgery. So the adversary has forged a MAC, has computed a valid MAC without knowing the key, and this is what we want to prevent. So if a scheme is secure, it should not be possible for an adversary to output a valid forgery, an M0 and a C0, such that the verification algorithm accepts those, even if the adversary had access to the box and saw some Macs before and saw some message, and so they had access to the verification algorithm as well. So this is the definition of unforgeability under chosen message attack for symmetric key authentication schemes. So the first thing that this definition tells you is that, so since we exclude in the definition this trivial attack where the adversary simply outputs a message and a code that I've seen before, this tells you that a Mac scheme alone cannot solve replay attacks. So what is a replay attack? A replay attack is an attack in which the sender sends some message, maybe with some code, to the receiver. The adversary intercepts this on the line, let this message be received by the receiver, and then later in time sends the same message over and over again. So imagine a setting in which you go to a shop and you do a transaction with your credit card, and then this credit card, and by doing that, you compute a Mac. When you input your card into the machine, your card computes a Mac on the message, please pay 100 krona to this shop. So of course you don't want that the day after. It would be very bad for you if the day after the shop could send the same message again and again and again. And then every day, maybe, after you've been in a shop, then every day from that day on, the shop can send a message to the bank, please give me 100 krona from Claudio's account. So this is known as a replay attack. So you have a message which is valid, and the attacker keeps sending the same message over and over again. Clearly, the Mac alone cannot solve this problem. Why? Because if the first Mac that you computed on the first day was valid, then the second Mac, the third, when you replay the same message with the same Mac over and over again, these Macs will still be valid, right? Because the Mac is just a function of the message and the key. So if it's valid today, it's also going to be valid tomorrow. So Mac schemes or secret key authentication alone doesn't solve replay attacks. To solve replay attacks, we will need to have something around it, we will need to have some extra mechanisms, and we talk about that at the end of this chapter. So what does a secret key authentication scheme does? It prevents forgeries. It is unforgeable, meaning that the adversary should not be able to produce a code on a message for which he hasn't seen a Mac before. It does not protect against replay attacks by itself. Okay, so for confidentiality, we saw a one-time pad, which was an unconditional secure encryption scheme. Similarly, for authentication, we'll have some one-time unconditional authentication solution, which is information theoretic, which is unconditional, meaning that it's secure regardless of the computing power of the adversary. But it's also, in the same way, completely impractical because the keys will be huge. So let's see how the scheme works. So the key generation algorithm outputs the follows. So the key in such a scheme is a number of codes, C1 to Cn, where each one of these codes is simply uniformly random TB strings. And you have one of these codes for every possible message that can be sent in the system. So let's suppose that you want to build a system in which you can send a single bit. Then you would have two codes. You would have C0 for when you want to send a bit 0, C1 for when you want to send a bit 1. If you want to be able to send a message from a larger space, then you would have one code for every possible message in your space. So let's say you have a system that is sending some measurement of some temperature or something, then you would have one different code for every possible numerical value which your system might produce. So these strings are uniformly random, are chosen uniformly at random by the key generation algorithm. And outputting a Mac is very simple. So if you have a message and you have the key, so you're simply gonna go and look up in this table the code corresponding to your message M, and that's the Mac you're gonna output. The verification algorithm is similarly very simple, and simply it takes as input the key, which is this table, message, and the code, and now it's going to check whether this code is the right one, meaning that it's the one in the table indexed by the message M. So if they're the same, it outputs accept. If they're different, it outputs reject. So it's clear that if you send the right MAC, the algorithm will accept because it's the same value in the table of the sender and the receiver. And now let's argue about the security of the system. So suppose that an adversary has seen the MAC for some messages, maybe 1, 5, and 7. So now what is the probability that the adversary will be able to forge the MAC for message 2, for which has not seen the MAC before? Well, the MAC for string 2 is a uniformly random TB strings, which is in particular independent of all the other strings that the adversary has seen already. So since all the codes are random and independent, seeing some of these Cs does not help the adversary in guessing the others. So the probability that the adversary will guess the right code, for instance, for message 2, if he has not seen the code for message 2 before, is going to be 2 to the minus t, where t is the length of the MAC. So this is interesting because whereas when we're talking about confidentiality, one-time pad was perfectly secure. Perfectly secure meaning that the adversary had zero advantage to win the security game. The adversary had probability 0 of guessing the right of decrypting the ciphertext. Here instead we have that the adversary with some probability might be able to guess the right MAC even if he hasn't seen it before. The probability can be made exponentially small by choosing t to be large enough. So for instance, if t is 64 bits or 128 bits, then 2 to the minus 64 or 2 to the minus 128, it's a number which is so small, then this probability is so small that we call it negligible. And in cryptography, we often have these probabilities which are negligible, so things that are in the order of 2 to the minus 60, 2 to the minus 80, which is simply have to live with, but it's perfectly fine because, I mean, an event that happens with probability 2 to the minus 28 or 2 to the minus 64, you're never going to observe this in your lifetime. Right. So this also shows, immediately tells us that any other MAC that we're going to show, we're going to look at afterwards, will have to have the property that the length of the MAC is long enough to prevent this guessing attack. So no matter how secure your MAC scheme is, even in the unconditional secure scheme where non-computational assumptions are done, so regardless of how secure your MAC scheme is, the MAC will always have to be long enough such that it's hard for the adversary to guess it. So this is something that we have to live with. So the problem of this one-time truth table, it's like in one-time pad, is that the size of the key depends on how many messages you want to authenticate. So the table grows really, really large with the number of messages. So the solution is completely impractical. I mean, think of if you want to authenticate some communication between you and a website. Think of the number of possible messages that the website might send you. This table is simply too big to be meaningful. So maybe a little anecdote here, a story. A few years back, this solution actually was used in a simple application in which it was easy to predict the number of messages which had to be sent. So the solution, the problem was the following. I believe it was in the context of handball, where they wanted to design a ball which would automatically detect when it was entering the goal, such that the referee would not have to guess whether the ball was inside the goal or not. So of course there is a lot of engineering problem here. I mean, how do you detect that the ball is inside the goal or outside the goal? And that's not a problem for cryptography. The problem for cryptography is the following. In a solution like this, you would imagine that the ball or the goal can send some information to the referee. The referee maybe has a smartwatch on his wrist that shows him, hey, there was a goal. So the communication between the goal and the referee's watch has to be authenticated. You don't want someone, maybe some very smart fan who knows about authenticity. You don't want them to send a message to the watch that like my team has scored a goal. So there should be some authentication mechanisms that prevents other people than the goal to send the message to the smartwatch of the referee. So in this case, since you can kind of predict the number, you can predict a number of goals that, the maximum number of points that can be scored in a match. You can make a table which is relatively small, where you simply have a table with all possible messages which will be sent during this match. Goal 1, goal 2, goal 3, goal 4, goal 5, goal 6, up to goal 100 or how many you need, which is still like a very small, which is a relatively small number. And then for each of these messages, you have a MAC which is maybe 64 bits long or something like that. And now this is a very efficient and very secure solution that can be useful in an application like this. So maybe it's not very useful for internet communication, but it could be useful for some niche application like this. Okay, so since these applications, these unconditional secure MACs are not very good for for internet communication or for other applications in which you have large bandwidth, we're going to have, like for encryption, we're going to have a MAC schemes where the key length is fixed, and where with the same small key length, you can compute MACs on a very large number of messages. So here again, let me stress that MACs are not encryption. MACs are not supposed to hide anything. The MAC is there only to authenticate the message. The MAC is there to make sure that the message cannot be tampered with. The MAC is not there to hide the message. In fact, the message is sent together with the MAC, so the message is not hidden. If you want to also hide the message, then you're going to also have to use encryption. But the two things are orthogonal. Since the MAC doesn't need to hide anything, MACs in general do not need to use randomness. And finally, C in these slides doesn't stand for ciphertext, but stands for code. So like in encryption, we already have these two necessary conditions for MAC security. So if the MAC scheme that you're going to use as a fixed length key and the same key is used for a large number of messages, then you will still have the exhaustive key search attack that we saw in the confidentiality lecture. So even for MACs, the attacks will be exactly the same. I mean, if the adversary sees some message and sees the MAC on these messages, which the adversary might have eavesdropped over the channel, now the adversary can try to find the key which maps these messages into these MACs by simply trying all possible keys. Since this attack is always possible, this implies that if you want a MAC to be secure, the key should be large enough such that this attack becomes completely infeasible in practice. And therefore, even in MAC scheme, even when we talk about MAC, the key has to be large, like 120 bits or more. The other attack, which is completely generic on any MAC scheme that we just described, is the guessing of the MAC itself. So you don't need to guess the key. You just guess directly the MAC for the message you want to send. So this is completely generic and even works for the unconditional secure MAC schemes. And this implies that the size of the MAC itself has to be large, like 64 bits or more. And this is to prevent that MACs are guessed. And this is unlike encryption. So in one-time pad, where if you were encrypting 1 bit with one-time pad, your ciphertext will be a single bit. But if you want to do an unconditionally secure, if you want to do a MAC unconditional or non-unconditional secure on a single bit, the MAC will still be at least 64 bits or more. And note that in some application, I mean, if you want to send bits one by one, then the bandwidth that you have to spend for these MACs will actually be significant. Right, so let's see how to build MACs with computational security. One very popular choice for computing MACs, computationally secure MACs, is known as Cbc Mac. So Cbc Mac, again, Cbc stands for Cipher Blockchain Mode. So this is very similar. This graph is very similar to what we saw in the lecture on confidentiality, but it's also quite different. So Cbc Mac is an algorithm that allows to take a long message, a short key, and produce a short MAC on that long message. So let's first decode this graph, and let's see how is a Cbc Mac computed. So you start with the first block of the message. So you have a long message, which might be a megabyte, a gigabyte, or whatever you want. You split the messages in blocks. Every block is 128 bits, or whatever the size of your block cipher is. So in this case, AES takes as input blocks of 128 bits. So you split the messages in blocks. You might need to do some padding in the last block. You input the first block of the message into the AES, get this an output. Now you XOR the output with the second block of the message, and you go on, and you go on, and you go on, until you get the last block, which is the output of AES applied to the last block of the message, XOR with the second last output of AES. The MAC is this last block and only the last block. And now you can send this message together with the MAC to the receiver, to the verifier, and the verifier will check that the MAC is valid simply by rerunning the algorithm in the same way. So we take the message with the key, compute this cascade of AES XORing the output of block n with the input of block n minus one, n plus one, until you recompute the same the final block and check whether this is the same as the one which was received. So now let's look at the differences between CBC Mac and CBC encryption. In CBC encryption, you had an initialization vector, which was here. The first block of the ciphertext was initialization vector, and that was XOR with the first block of the message. This is missing here because Macs do not read randomness. They're not trying to hide anything. So it's perfectly fine that if you compute the same, the Mac on the same message twice, you get the same Mac. That's perfectly fine. In fact, you need that property even for verification purposes. So essentially, CBC Mac is like CBC encryption, but where the IV is set to 0. And the second main difference is that in CBC encryption, you would output all the output of all the AES blocks, because all of these were needed to recompute the message. The ciphertext was as long as the message, and you would need all the blocks to recompute the message. But in CBC Mac, we're not decrypting, we're only verifying. So we only need the last block. You don't need all the intermediate blocks. So those are the differences between CBC Mac and CBC encryption. The graph is similar, but it's very different. What is very different is that the goal is very different. In one case, you're trying to hide a message. In the other case, you're trying to authenticate the message. And then the algorithm itself is different. In one case, you have an initialization vector, and you output all the blocks. In CBC Mac, instead, you don't have initialization vector, and you only output the last block. The security intuition is, why is this secure? Why is this CBC Mac secure? The idea is that this last block depends in a very complicated way on the entire message and the key. So suppose for a second that the adversary sees this cipher, this Mac on this entire message and wants to compute the Mac on a different message. Maybe a message in which the second block here differs by 1 bit. So maybe the output of the first block will be the same, but then when you XOR that with the block where there is 1 bit of difference, that 1 bit of difference here will be input to AES, which behaves like a random function in some way, and therefore the output will be very different from the input, and that this large difference will be propagated. So this is, for instance, a very easy question that you might think about right now is, why are we using the last block of this as a Mac and not the first block of the Mac? Think about it for a second. Pause the video if you need. So if you were using the first block as the Mac, right, then the Mac would only depend on the first block. If you had now, if the adversary wanted to compute, could easily change the message, maybe change the last block, and then the Mac could not change because the Mac was only a function of the first block. So clearly the Mac has to be a function of the entire message, and it has to be a function of the key.